Hello class, welcome back to Introduction to Material Science Engineering, and today's lecture topic is composites. This is going to utilize this lecture, or the topics in this lecture are going to utilize principles that we've looked at for monolithic and especially multi-phase materials from our heat treating and our strengthening discussions in the past, since composites are basically a fabricated way of achieving what we could otherwise achieve spontaneously with different microstructures, as well as giving us combinations that we couldn't have gotten spontaneously. So just to define composites, they are combinations of one or more individual materials that are combined together to obtain properties superior to what any of those individual materials could give on their own. So it's a best of material, and most of our processing errors will result in getting the worst of. So that's something that has been or will be discussed in our processing section. Two main parts of a composite: the matrix, which defines the continuous phase, which we saw if you've listened to or read any of the discussions on heat treatment and microstructure and metals, is very important because it tends to define many of the properties. That is less so in composites, but the matrix still plays that important role of connecting the reinforcement together and, most importantly, transferring load. The reinforcement phase, or the reinforcement portion of a composite, is the second part, and it basically does whatever the matrix cannot do, and does it while still being discontinuous in most cases. Some of the fiber reinforced composites include reinforcement that is quasi-continuous, especially long fiber or sheets or wovens, but in most cases the reinforcement is discrete, non-continuous. Okay, we have a little flow chart at the bottom that basically breaks down the types of composites based on the size and continuity of reinforcement and also the manufacturing complexity. So starting over on the left, we have particle reinforced. So this would be where the reinforcement is more or less equiaxed, generally fairly small. We do have large particle reinforced composites. This would be maybe a gravel aggregate in concrete would be an example of that. But the majority of particle reinforced composites are smaller scale reinforcement, which would be towards the end of dispersion strengthening, like we saw in dispersion strengthened metals for high temperature use. In fact, those are dispersion strengthened composites, albeit spontaneously formed, and they would probably represent the small end of the scale of your dispersion reinforcers. The most common composites encountered are fiber reinforced, and this is for a reason. It's because we can use the anisotropy of the fibers to give us preferential properties in a direction we need them, and not have to include quite such a high level of reinforcement in every direction. And so the fibers can either be continuous, aligned, which will mean they will have to be aligned, or they can be discontinuous, short, such as chopped fibers, and in which case they can either be aligned or they can be randomly oriented. And again, that will be determined either by the cost of the processing or the need to have isotropic versus anisotropic properties. Over on the far right, we have laminates and sandwich panels. These are called structural composites, and they are actually manufactured subcomponents that can either include combinations of other composites, fiber reinforced, or they can include combinations of monolithic materials that are assembled usually with adhesives to transfer load very evenly across intercomponent interfaces. And again, the goal is typically to get very, very high strengths, usually in one or two directions, with very little weight. So the sandwich panels and structural laminates are typically used, especially when they're multidimensional, or used for lightweighting applications. Okay, I mentioned that matrix and reinforcement are the two components of composites, and they also are the manner in which composites are classified. So if you're looking for information on a type of composite you might think of looking for, and you're out in the literature or vendor information looking for some specs and properties, you want to go by these categories. First of all, composites are classified by the matrix as the first classification, so you'll hear composites referred to as either metal, ceramic, or polymer matrix composites. And so that's the MMC, CMC, and PMC. So the matrix is the first way they're categorized. And then secondary to that, the reinforcement phase may or may not be called out. What you need to remember, and is a lot of common sense, is that the reinforcement phase in each case will be chosen to basically give you whatever properties the matrix is universally lacking in. So in the case of metals, they tend to be pretty good across the board, and your reinforcers will usually be added in order to increase the properties in a single direction. So you'll add a ceramic or maybe a carbon fiber to increase modulus in one direction, to increase yield. Definitely if you include a refractory reinforcer in a metal matrix composite, you have the potential for improving your thermomechanical properties like creep and stress relaxation resistance. Ceramic matrix composites will have a reinforcement phase that achieves one objective, and that's increasing fracture toughness. Ceramics generally have plenty high modulus. They are reasonably lightweight, especially compared to metals. They tend to be quite strong, albeit they have very low elongation at failure. Our main design constraint with ceramics is their low fracture toughness. So the aim of pretty much every ceramics matrix composite is to improve on that so that we can actually put them into service and gain the benefit of all those other properties. So the reinforcement phase will do that, usually in a couple of ways that we'll get into in the next few slides. Polymers, kind of the opposite of metals. A polymer matrix composite is going to be effectively very weak, has low creep resistance, low thermomechanical properties, because that's the weak point of polymers. So your reinforcers will be looking to improve on all of that by basically selectively accepting the load applied to the material and bump up modulus, bump up tensile strength, and bump up creep resistance while not adding much weight, since we'll want to be preserving that good property of our polymer matrix. Okay, so here are some graphs which basically display the benefits of the reinforcers on their respective matrix phases. We're going to start up in the upper left with ceramics matrix composites and just basically show the evidence of increased toughness with a bend displacement test. So this is like a 3-point or 4-point bend test, which is evaluating the fracture toughness of a ceramic. How far can we deflect it in bending before it cracks? So if you look at the purple plot of force versus displacement, that's the monolithic unreinforced ceramic. If we put a particle reinforcer in, not only do we increase the modulus, we also increase, in this case, force, which would correspond roughly to a stress at failure, and haven't necessarily changed the strain at failure very much. But if we were looking at fracture toughness, remember, it's the area under that curve. So even though the strain at failure is the same, we've actually increased the energy that material could absorb per unit volume. And the actual mechanism that allows those particulate reinforcers to do this is crack deflection. You might still have a crack slowly propagating through the material, but it has to change direction every time it hits one of those particle reinforcers because it's difficult for a crack to cleave those. So this is fairly akin to the idea of a dislocation having to move around a dispersion strengthener, except this time it's a crack. And the more times a crack changes direction, the more surface area that it has to liberate and the more energy that is required to keep it propagating. In the case of a fiber reinforcer of a ceramic matrix composite, we see a little bit different behavior. That's the sort of aqua blue line in between the two other curves. In that case, we initially get a higher modulus than we would the unreinforced ceramic, but at some point that modulus heals over just a little bit. We get a flattening of that slope, even though it's still a straight line. That represents the point at which we've exceeded the capacity of that ceramic matrix and started to crack it. And so we've started to lose cohesion between the reinforcement and the matrix, but we still have enough to carry the load and transfer it. And you begin to see now the fiber carrying all of the load until it starts to fail. And then the failure, this is important, the failure is not abrupt, it's gradual. So from a fail-safe standpoint or a crack detection standpoint, that's very important. We're not going to get catastrophic failure with those fiber reinforcers. So even if we didn't improve the fracture toughness, which of course we did, that would be a tremendous benefit for safety and service. Looking to the right at the PMCs, or polymer matrix composites, again, the main goal there was to increase modulus while not also increasing density. Excuse me. So you can see the green circle towards the middle of the plot representing the unmodified, the unreinforced matrix of polymers. And so you've got a moduli in and around 0.01 to 1 gigapascals and a density of right around water, a little over 1 milligram per cubic meter. And as we move over, as we add some reinforcers, particulate, fiber, and different types, we could add other polymers like carbon fiber, we can add ceramics, we can add metal wires or metal fibers. We can get somewhere around 2-3 orders of magnitude increase in modulus with less than an order of magnitude increase in density, with the highest being with addition of a metal reinforcer there in the red, and a big range on that. Metal matrix composites, we're looking at addition down on the bottom center, looking at the effect of the addition of a silicon carbide whisker. This is a single crystal elongated reinforcer, basically an anisotropic crystal with a very high aspect ratio added to the aluminum matrix. This is distinct from a second phase precipitating out during heat treatment. This is a deliberate addition during processing, very easy to do with powder metallurgy. And you can see that in this case, we have strain rate plotted on the y-axis and stress on the x-axis, and the difference in slope and position is indicating an increase in creep resistance. Okay, so we're going to start with particle reinforced and go up through structural panels, look at a few examples, and look at a few aspects of the microstructure that affect performance. So we're going to start with particle reinforced and give a few examples here. The first two, honestly, are spontaneously formed. These are things that you might remember from heat treatment of steels and and some of our phase diagrams discussions. So if you remember spherodite, the long duration heat treatment product that comes from tempered martensite held at temperature below austenite temperature for long durations, that is actually an example of a spontaneously formed particle reinforced composite, where those cementite round particles strengthen the ferrite matrix. They're very fine dispersion, and so they can stop dislocations and also add a little bit of fracture toughness. Generally, particulate reinforced composites on this scale would be spontaneously formed through thermomechanical treatment of usually a metal alloy or a ceramic. You can add very fine powders to polymers, provided that you have matching surface energies, so you can add ceramic powders to a low viscosity polymer matrix and also achieve the same type of strengthening there. On the ceramic side, not that cementite isn't going to act like a ceramic, but a little bit more targeted type of high temperature ceramic, tungsten carbide. This is a precipitated tungsten carbide in a cobalt matrix. This is going to have very, very high thermomechanical properties, great for high-speed machining, very corrosion resistant in certain environments. And so in this case, the cobalt is the continuous phase, and it's shown in the very small bits of light color, and the tungsten carbide is the sort of the blocky phase. And in both of these cases, what you're looking at is an optical cross-section, a polished cross-section of the microstructure. very similar to what you saw on the phase diagrams, microstructural schematics. And the last one is a polymer in polymer particulate reinforcement. This is carbon black in rubber, very essential for automotive tires and many different rubber applications. In addition to being a mechanical strengthener, those carbon particles also contribute to good photocorrosion resistance. They're excellent ultraviolet absorbers, and so when they're added to a polymer used outdoors in a weathering application, they give it quite a bit of resistance to photolysis and photooxidation. Okay, fiber reinforced composites. These are probably the workhorse category for composites in general and really represent the opportunity where we can maximize on the differences in a matrix versus a reinforcer's characteristics. The thing to remember is if you are using fibers that are not randomly oriented, we're going to end up with a material that is very anisotropic. And that's because a fiber is by its very nature, if it's standing out by itself without a matrix, it's very, very strong in tension, but very weak in compression or shear. So if you took a carbon fiber and tried to bend it around itself, it might not have a very good bend radius. Again, depends on the fiber. Certainly a glass fiber might not. In general, the only reason that these have any kind of deflection resistance is because they're very thin, and they keep themselves by being thin in plane stress. So it goes back to our colder, faster, crowded argument of crack propagation. But that's essentially why fibers can be bent and processed in composites. But we don't necessarily want them approaching the limits of their bend radius in service, and so by using a matrix to fix them in position, we ensure that they are loaded in their strong orientation and their tensile orientation in the service environment within the material that we're manufacturing. So that's one of the big roles of the matrix, in addition to preventing scratching and just basically keeping the whole subcomponent together. It's holding those fibers aligned with their strong tensile axis towards the tensile stress state that the part will be subjected to. And of course, the secondary main reason the matrix is there is to transfer the load to the fibers, since you can't very effectively grab onto fibers, maybe at a transfer fixture on the end. Okay, reinforcement types. Basically got 3 different types, of which fibers, again, are the most commonly used. We'd mentioned silicon carbide whiskers in the 6061 aluminum example earlier as being an example of a ceramic reinforcement in a metal matrix composite. Whiskers are fairly expensive. They're high aspect ratio, thin single crystals, rather expensive to grow. They tend to be, again, ceramic in nature or graphite, very brittle. Very limited number of defects, dislocations, so they're very, very strong. They're not practical to use in huge volumes just because of their high processing cost and difficulty in handling. More often it is a fiber which is used as fiber reinforcement, not surprisingly because of the name. And these can be manufactured in mass, in bulk, much more easily. These are polycrystalline. They can either be crystalline or amorphous, typically crystalline, and in the case of polymers, they'll be aligned, chain aligned, such that those covalent bonds are all aligned in the axis of the fiber, and that's really what gives them their strength. This is definitely the case for the ultra-high molecular weight, high modulus polyethylene fibers, and also for most carbon fibers. Obviously, in the case of ceramics, we can get polycrystalline. We're not going to have chain alignment since they're networks, and they will, though, get their strength from the fact that they are covalently bonded, and the fact that, despite the fact that they are ceramics, that because they are so thin, they are in plane stress, so that defeats some of the fracture toughness limitations. Metal wires are used less commonly than fiber composites, but would have a role in things like reinforced concrete, a few selected high temperature applications. Okay, fiber reinforcement kind of comes in 2 flavors, continuous and discontinuous. So this slide addresses discontinuous fibers. You'll hear this going under the term chopped fiber quite often. You can have that discontinuous or chopped fiber randomly oriented and end up with a composite that is more or less isotropic or more isotropic in nature, or you can align those fibers and have something that's going to have more anisotropic properties, more akin to what a continuous fiber composite would have. Something important to remember about discontinuous fiber is that there is a minimum length of fiber, of those chopped fibers, that are necessary in order to achieve what you're adding a reinforcer to do in terms of strength and modulus modification. It takes a certain amount of length of fiber oriented parallel to the stress direction to effectively transfer load from the matrix. And this is going to be a function of the modulus match and the strength of the matrix to fiber interface. So the two diagrams on the bottom showing low and high fiber efficiency kind of give you an idea of that. You have stress being applied right to left, horizontal on the schematic. And in the case of the short fiber, which is said to have low fiber efficiency, those isostress lines that you see in the matrix that are running vertically in the slide indicate that the matrix is carrying most of the load at the ends of the fibers because it's the only thing there. As you move into the fiber, that stress gets transferred with distance from the matrix into the fiber along the ends. So right at the very end of the fiber, it's not really carrying any load. Stress transfers to the fiber by fiber length via its circumference. And so it takes a long fiber, fairly long, to transfer stress from the matrix. And there's actually a critical length. You can see here the equation for that that allows you the most efficient utilization of the strength of that fiber. So basically that critical fiber length formula that you see sort of near the top middle of the diagram basically ratios the interfacial strength of the fiber to matrix interface to the actual tensile strength of the fiber. And it says, here's how long the fiber has to be so that the matrix can transfer stress to it sufficient that I could break the fiber with the transferred stress. So if you are able to transfer enough stress that you can use the full strength of that fiber, as evidenced by you could break it, then you're getting the full efficiency of the fiber. And that's literally what that formula says. So since fiber reinforcers tend to be a bit on the pricey side, you don't want to use a higher volume fraction of them than you really need. Additionally, they will tend to be the things that make your composite maybe a little bit more dense, and so you want to use them sparingly. On the other hand, you're using them for a reason. You need them to do their job. So volume fraction of fiber and fiber length are two different independent variables that you typically can choose from. So if you're adding a fiber reinforcer to achieve higher modulus or higher strength, there is that minimum length that you need to be effectively getting your money's worth from the reinforcer. And as a rule of thumb, just a quick benchmark for glass fibers, for typical diameter glass fibers, you'll need about 1.5 centimeters of length in a chopped discontinuous fiber matrix composite to achieve that. Okay, last category is structural, and this is sort of a 3D or a manufactured good composite. The simplest of these is a laminate, where we would have basically just literally a stack of fiber reinforced composites that are oriented at orthogonal orientations, 90 degrees to one another. And so as we change the orientation around the coordinate axis, we can effectively achieve something that's quasi-isotropic, especially if they're not very thick. Sandwich panels are far more complicated, and in this case we have what could be just monolithic materials, a face sheet, it could be a continuous piece of plastic, a thin layer of metal, and then we'll have an extruded or possibly additive manufactured core, usually in a honeycomb or other kind of hollow, lightweight structure. And then they're adhered together with structural adhesive. This is so that the load can transfer very uniformly. And all of these pieces are very, very thin. The laminated, glued sandwich panel has mostly void space, and the components that it has within it are strong in two orthogonal directions. And it's very thin, so it can't really deflect much in shear between the two faces, and so that's really what gives its structural integrity. Again, possibly some of those subcomponents could themselves be composites with fibers, but the general advantage could be achieved even with monolithic materials. Okay, these are some very, very simple schematics of different types of composite processes, starting with something that this is typically a low manufacturing volume process, a layup. This can be adapted to mass manufacturing and rapid manufacturing, but basically it would involve a sheet or a tape of a woven fiber composite, usually pre-impregnated with its polymer matrix, an epoxy or phenolic that is partially cured so that it's handleable, and it's laid up in a mold, or in the case of a tape wrap composite, is actually wound around a mandrel with a release layer, and then the entire assembly is usually vacuum bagged and cured in a hydroclave or autoclave. It's very thin, and the matrix is a UV curable adhesive or UV curable polymer. You would have that as an option for the cure, but typically these are heat and catalyst induced cures that will basically achieve the full matrix strength. So this is a cross-section of a vacuum-bagged laminate composite. So where the little block saying laminate is your actual workpiece. So it's laid up on a rigid backer, usually a big piece of metal, and then a porous, what they call bleeder cloth, fairly thick textile, is placed over it, and then the whole thing is sealed with an impermeable bag, and a vacuum is applied between the bag and the bleeder cloth. The bleeder cloth prevents that vacuum bag from pinching down, and it ensures that the entire cavity is evacuated, so we effectively have 1 atmosphere of pressure being applied to the entire assembly during its cure. This has a couple of advantages. First, it applies a little bit of pressure normal to any of the interfaces that we might need to achieve adhesion on within that laminate. Second, if there are any gases being produced during the curing reaction, it assumes that they continue to evacuate, and we don't put any back pressure on the cure reaction, chemically speaking, and we achieve a good full cure. And third, it ensures we have good heat transfer if we're doing this in an autoclave, for instance, and we need to uniformly raise the temperature, although typically that will be achieved through that big metal backer plate if it's all placed at elevated temperature in an autoclave. If we need more than 1 atmosphere of pressure, we have the option of placing all of this in a hydroclave, where we can use the incompressibility of a fluid applied over the top of that vacuum bag to basically ramp up another state variable, increase our pressure, something that we haven't really discussed as a processing state variable till now, but this would be one example where we would not work at 1 atmosphere of pressure if we needed the high pressure from a hydroclave. Kind of going to the other end, we can process in tension, especially if we have a continuous fiber. So we can unwind maybe a slightly pre-impregnated continuous fiber from a spool. This is very advantageous for textile fibers like Kevlar, HMPE that are quite flexible in their non-impregnated state. We will add more matrix resin as needed before winding onto a mandrel, and then, of course, finishing the cure either in an oven or, if possible, at room temperature. Because we can achieve most of the fiber orientation in the hoop direction, these are obviously very valuable for pressure vessels. So you'll see pressure tanks made of these filament wound arrangements, and of course they'll have to bend around in 3D around the ends so that we can quite often have it continuous in sort of an ovalized 3D shape. If instead of pulling a fiber and winding it, we pull it through a resin bath and then cure it in any given shape, this is a process called pultrusion. It's effectively similar to filament winding, except it's more axis symmetric. Typically, the fibers are cured in a straight configuration rather than winding around something, but otherwise has the same idea, that we're starting with something flexible, one or more fibers. We can blend those together, have different types of fibers, but the key is to have them go through a thermoset resin bath in its liquid, non-cured form, and that gives us our matrix. We preform it. This is usually all done under a certain amount of tension, and then the composite is actually achieved as that assembly of fibers and uncured matrix polymer goes through usually an oven and cures, and then you have an actual composite once the matrix cures. Typically cured by heat or by time from immersion in the resin bath with a catalyst. UV is an option depending on the resin type and how thick it is. If we have a particulate composite, we have the option of, depending on how viscous it makes our resin, we have the option of pumping a thermoset resin, especially a two-part that achieves its ability to cure when the parts are mixed together, of doing an injection mold. So we'll have a base resin and a curative with whatever kind of pumpable particulate reinforcer in two tanks. Those are pumped into a mold and mixed during the pumping, so it's very important to get these mixed very well, because if it's not mixed well, it won't cure. And then we'll have uncured spots that don't achieve mechanical properties. We can apply heat to the mold to help the cure, make it cure faster or make it cure more evenly, and then take the mold apart. So we could achieve a process very similar to a thermal injection molding for thermoplastics, or for permanent mold or injection mold casting of metals, except rather than a solidification process or a cooling process down below TG, it's actually the cross-linking or the network polymer formation that's actually achieving the material properties. If we partially cure, so that we have a little bit of what we'd call green strength of the material, or if we go with a long molecular weight polymer that has some properties, it's viscous and it is basically self-supporting, and then we want to cross-link it a bit more after the fact, we can use compression molding. So in this case, our workpiece is labeled in the red little square called a charge. So this would be our what we call a green piece. It has some strength. It's sitting there. It's not pumpable the way the two-part reaction molding charge was. So it can sit in the mold, and this would be akin to high temperature forming for metals, where we mold it into place, and then by cross-linking it in situ, usually at high temperature, we achieve both shaping and properties at the same time. And this can be done in a fairly short cycle. So that is it for composites. We've hopefully touched on a lot of properties that you've seen prior in the class: microstructure, transfer from matrix to fiber, when to use a particulate isotropic type composite when we need the selective anisotropy of a fiber composite, and then a few methods that are specific to polymers or specific to thermoset polymers for processing. Again, there are specialized high temperature composites that would follow more of classic ceramics processing or metal processing. We didn't go into those today. Those are really the exception. The polymer matrix composites definitely represent the majority of composites in use today. And so we've captured a lot of the workhorse methods that are used to make those. We'll see you again for the remainder of the lectures in this class.